This is session D7 on Schrodinger's cat. Last session, D6, we talked about photon entanglement, state collapse, quantum reality, the Einstein-Podolsky-Rosen EPR paradox, Bell's inequalities, local realism, quantum non-locality. Today we'll explore Schrodinger's cat. This is a short video and this is the final video in this lecture series. Schrodinger published his Schrodinger's equation for quantum mechanics, wave mechanics, in 1926. Months later, Max Born published his interpretation that the magnitude squared of the wave function represents the probability density for finding the particle at a location and time, replacing determinism at the atomic scale with probability, which has since been called the Copenhagen interpretation of quantum mechanics. Einstein wrote a letter to Born, a portion of which later became paraphrased as Einstein being convinced that God does not play dice. Niels Bohr later responded to Einstein advising him to stop telling God what to do. In other words, let's see what quantum mechanics says about physical reality, compare it to experiments, and not interject philosophy a priori, or our expectation of what reality is. We should measure reality. After he published his equation, Schrodinger expected that solutions would give deterministic positions of particles, more like a classical wave. Neither Einstein nor Schrodinger were comfortable with the Copenhagen interpretation and giving up determinism at the atomic scale. Concerning the probabilistic interpretation, Schrodinger said, "I don't like it, and I'm sorry I ever had anything to do with it." In order to question and clarify the Copenhagen interpretation, Einstein had an idea for a thought experiment, and Schrodinger published this in 1935 as his Schrodinger's cat thought experiment, which we will now explore. This is a possible time to take a break. In this thought experiment, Schrodinger places the following items into an opaque box and then closes it for a fixed amount of time. A living, healthy cat. One radioactive atom with a decay half-life T1/2. An ideal perfect radiation detector surrounding the radioactive atom. If the atomic nucleus decays, the detector will detect it. A glass vial of poison gas. If the detector detects the radioactive decay, it actuates a hammer that breaks the glass vial, releasing the poison gas, and the cat immediately dies. So here's what we have inside the box. I'm taking this from this website. It was created by author D. Hatfield, and I have not modified it. So there's a radioactive atom, a detector, an actuator, a hammer that can break a glass vial of poison gas, and a living cat which would be dead if the poison gas got released because the radioactive atom decayed. The opaque box remains closed for the half-life of the radioactive nucleus. When the half-life has passed, we open the box. There's a 50% probability that the cat is alive and 50% probability that the cat died. Before we open the box, we would say that either the cat is alive or the cat is dead. But how does quantum mechanics describe the state of the system in the box just prior to our opening the box? If quantum mechanics applies to macroscopic systems and living systems, then the wave function of the system in the box immediately prior to opening the box would be wave function of the system is 1 over square root of 2 times a wave function for the alive cat and a wave function for the dead cat. 1 over square root of 2 because there's 50% probability of the cat being alive or dead at the moment we open the box. This wave function represents the contents of the box as an equal superposition of the cat being alive and the cat being dead at the moment the box will be opened. A superposition of alive and dead prior to measurement, opening the box, which is a different way to say it than saying the cat is either alive or dead. The apparent absurdity of this alive and dead situation is what Schrodinger intended to ridicule by this thought experiment. In his mind, clearly the Copenhagen interpretation of quantum mechanics had led to an obviously absurd description of macroscopic reality, as Schrodinger intended to ridicule. However, the apparent absurdity of the wave function being a superposition of living cat and dead cat did not kill the Copenhagen interpretation or quantum mechanics. 85 years later, the Copenhagen interpretation is still the standard interpretation, and physicists still have no better interpretation for the state of Schrodinger's cat than the alive and dead superposition. This feels incomplete, unsatisfying, and to contradict common sense or at least common language, but it is what it is. Physicists continue to do experiments to determine to what extent quantum mechanical observations can partially look into a closed box without changing the internal state, and new results could come in your lifetime. The Copenhagen interpretation of the quantum mechanical wave function and the probability density is the standard interpretation of quantum mechanics taught in courses and books. There are alternative interpretations which we won't cover, but you can find on this Wikipedia page, Interpretations of Quantum Mechanics. As far as I know, there are no known experiments whose results can rule out some of the alternate interpretations, such as the many worlds interpretation. So no known experiments to prove that the Copenhagen interpretation is the only correct interpretation. Physicists' and chemists' use of quantum mechanics generally follows the shut up and calculate mode. So quantum mechanics is used to predict the results of experimental measurements. Experimental measurements are done, and it's seen whether they agree with the quantum mechanical theory of the problem. Thinking about the interpretations of quantum mechanics may be considered philosophy rather than hard science. However, you're free to make up your own mind on the interpretation and on why quantum reality is the way it is. But all experiments agree on the what of quantum reality, regardless of our difficulty pondering the why. So, even if you ponder the different interpretations of quantum reality, try not to extend that to question whether quantum mechanics correctly predicts quantum reality. It does. This is the final lecture in my lecture series. Thank you for watching. I hope that you have learned a little about quantum mechanics and this was worth your time. I created this lecture series hoping to reach two audiences: high school students and undergraduates who would likely not take a quantum mechanics course, but who wanted a brief introduction, in particular with little or no calculus. Adults continuing their education or senior learners who want a brief introduction to quantum mechanics. If you enjoyed this course, I ask you to find one friend or acquaintance to recommend this course to. Thank you. If you have watched all or most of my lecture videos, then very likely you could progress to one or more real online course on quantum mechanics if you like. edX has several excellent courses on quantum mechanics which you can audit for free. Quantum Mechanics for Everyone from Georgetown is very interesting. It addresses some of the mysteries of quantum mechanics, and it does not require calculus. MIT's 804 and 805 series are what their undergraduate physics students learn. They're excellent courses if you know calculus and you're comfortable with differential equations. There are also good courses from Stanford and Harvard. Thank you for watching this lecture. Good luck to you. This is the end of Lecture D7 and the end of this Quantum Mechanics lecture series.